Earth Calling Thermo students. Earth Calling Thermo students, come in. Hey, Spencer is with me. How about that? Good deal, Spencer. So it's just you and me, yeah, right now. How are you today, Spencer?
No major complaints.
As they say in the Ozarks, it's tolerable. Okay, well, I'm just waiting for a few more customers here. You know, this is our last week together of our summer class. And you're going to take your final this end of the week, and then it's going to be over. Let's see if there's any other customers here. Nope, it's just you and me, Spencer. Spencer, do you have any questions for me?
Can you tell me a little bit more about the final, like when it's going to be posted, when it's going to be due, stuff like that, so I can sort of plan my schedule for my other class around this?
It will be posted Wednesday morning at 8:30 a.m.
Okay.
and it will be due Saturday night when the clock strikes 12, kind of like Cinderella at the, didn't she turn into a pumpkin or something like that?
Something like that.
Yeah. But that gives you plenty of time.
And when you say, is that Saturday at midnight, like the beginning of the day Saturday, or the end of the
No,
day Saturday?
it's the end of the day Saturday.
Got it.
Yeah, I guess it's the beginning of the day Sunday is what it is.
Gotcha.
So you'll be all right. Was there some other question? Was there?
Um, I see the one assignment posted that's due tonight. Is there
Yeah,
another assignment that's due Wednesday?
yeah. I think there's another homework assignment. Uh, the last one. I think there's one more homework assignment, and it might be due Wednesday.
Okay.
I could check on that. That could be wrong. Let me look and see here. I probably have that here someplace. Yeah. Yeah, what is the 23rd? That would be,
Thursday.
yeah, I bet it's due the 23rd, but don't quote me on that. But it'll say on Blackboard what it is.
Yeah.
So that's your last homework assignment. Hey, it's 8:30. Let's see. Let's see if anybody else is showing up here. Oh yeah, we got a good crowd here. Look here, there's Stuart and Aubrey and Spencer so far. But you guys all know that even if nobody showed up, I would go ahead with my lecture. And the beautiful thing is you could watch it on YouTube. My daughter puts those on YouTube for you guys. Let me ask somebody. I'm always picking on Stuart. Stuart, have you ever watched one of my wonderful YouTube lectures?
I have.
It was wonderful, wasn't it, Stuart?
Yep.
Hey, Cameron is with us now, too. Good deal. Okay, well, let's just go ahead and launch into today's work. Now, today we're going to study really the last new topic, and that's the Stirling cycle. And then really, I'm going to go over some review stuff to prepare you for your final. And then Wednesday, I don't think we're going to have anything new. It might be new to anybody that hadn't been paying attention, but I'd like to go over some of the important things in the course on Wednesday. But right now, the topic is the Stirling cycle. And the Stirling cycle has, what we're talking about, the Stirling cycle, it has two isotherms. And two isochores. I wonder if I'm writing big enough to where you guys can read that. Maybe. I think you could probably read that. Let me find another one. This one's not dark enough. So here, let me draw it for you. We're going to draw a Stirling cycle. Now we're dealing with air here. It doesn't have to be air, but it'll be an ideal gas. So we don't need a vapor dome. Don't put a vapor dome on the Stirling. Okay, we could put isotherms on there though. Let's do that. There's an isotherm. There we go. And there's another one. There we go. So we have two isotherms. We have a hot one and a cooler one. See this, the one here is hot. They get hot going out this way. And then you have two isochores. And they kind of go like that. So if you start here at 1, you go up this isotherm here to 2. And then you go up this isochore to 3. And then come on down here to 4. And then down here to complete the cycle, you're back to where you started. It's a cycle. It's a Stirling cycle. See, this is compression here because the volume's getting smaller. And then what are we going to call that? Well, there's a ignition there. There's a heat transfer in somehow. You have to have some fuel. These heat engines don't work unless you fill up the tank with gas or whatever it is you're using for fuel. So you have a heat transfer in there. And then 3 to 4 is your power stroke, but there's a heat transfer in there too. You could label these. This would be Q34. That would be Q23. And then there's a heat transfer out here. There's 4 heat transfers. This one's Q41. But we don't speak of exhaust because the Stirling cycle is in a control mass. There's no mass coming in and there's no mass going out. It's a cylinder, piston cylinder situation. Now here's the heat transfer during compression from 1 to 2. There's 4 heat transfers. Okay. and it's a control mass. So you would use the control mass version of the first law, wouldn't you? All right, well, let's do one. Any questions so far? Well, I think the one I want to do is 1081. Let me find it. Chapter 10, number 81, says here, ideal Stirling cycle. You were doing an ideal Stirling cycle. Now you have to know that they have real Stirling cycles out in the real world. They exist. They have Stirling engines. They've had them for years and years and years. They've had them in the oil field for running oil field equipment. They've had them on boats. There's even a Stirling engine. It's actually a refrigeration cycle on the space shuttle, I understand. So this is a real thing. It exists in the real world. Now this one uses air, and it says here we start with 50 degrees Celsius. So here, let me write that. This is 50 degrees Celsius and 100 kilopascals. So over here, that's 100 kilopascal. Compression ratio is 6. Well, let's make a note of that. R equals 6. In other words, V1 over V2 is 6. You could write it like that. You could say V1 over V2 is 6. Maximum temperature is 900. Well, that's this one here. This is the 900 degrees Celsius. See, the low temperature is 50, the high temperature is 900. Calculate the maximum cycle pressure, we'll do that, and the thermal efficiency, we'll do that with and without regenerators. Well, we'll explain what regenerators are in a little while. This engine, if I remember, was invented before the Civil War, 1846, I think. But don't quote me. You could look it up on Google. But it's been around a long time. And for a while there, in England, it was invented in England. For a while there, it was in competition with the steam engine. Now, they had the age of steam, but if the Stirling engine had been favored over the steam engine, it would have been the age of Stirling. But the steam engine was preferable, and I'll tell you why here later. But let's go ahead and work our problem now. We're going to do problem 1081. And you know how I like to do these. We have so much fun doing these tables, these property tables that have energy transfers. And we're going to do a Stirling cycle. P, V, T, and delta U, Q, and W. There we go. Now this one is in SI. It would also be fun to do one in in English, wouldn't it? I bet you guys would like that too. Okay, well now according to the problem, we're going to do 1081. If somebody just showed up, we're doing a Stirling cycle. Let's see if there's any new students that showed up here. Let's see. Parker, yay, Parker showed up. We got a good crowd here. Anyway, we're going to do problem 1081. It's a Stirling cycle. And they said at state 1, temperature is 50 Celsius. We might have to change that to Kelvin later, but it's okay right now. And then the pressure is 100 kilopascals. Kind of ran out of room there. Let's see if we can squeeze it in here. Kilopascal. Okay, let's take time out. And what I want you to do is to find the specific volume. Okay, go for it. It's state 1. Don't forget, it's got to be in Kelvin or it's no good.
Are we using air for this?
Yes, this is air. We are talking about air. But thank you for asking. Well, I got an answer. I'm not at all sure it's right. Let me do it again. Well, I got an answer. Did anybody get 0.9274 cubic meters per kilogram?
That's what I got.
I bet that's right. We're off. We're doing great. Now, if the compression ratio is 6, then you can get V2, just divide that by 6. Here we go. We're going to divide that by 6. Get your calculator. 0.9274 divided by 6. I'm getting 0.15. We could round it off to 46. Hey, did anybody need my help to get that? Ooh, I'll write it out if anybody wants me to. Just speak up.
I'm having some trouble finding that.
You had trouble finding that?
Right.
Let's write it. Here we go. You go P1 V1 is equal to R.
I was looking at for a table. That's why I couldn't find it.
Oh, okay. You're all right then, right? You're okay?
Yeah, I can do that part.
Yeah, I know you can. I know you can. But your impulse was good. You should always go to the table if there's a table, but see, you have to use ideal gas on that. Okay, well, we got the V2, if you understood that. Now here's the beautiful thing. V2 and V3 are the same, so you can fill those in. Look at there. Isn't that nice? Not only that, I can fill in V4. V4 is the same as V1. Can you guys see that? It's 0.9274. Any questions? Okay. Now, what do we know about these temperatures? Well, see, state 2, you know what? The temperature at state 2 is the same it is at 1. You're going to like this. This is a nice little problem here. It's easy. And see, the temperatures at 3 and 4 are both 900. Now, we did these in degrees Celsius. That's fine. You have to put it in Kelvin though when you use the ideal gas law. Okay, now we're going to take time out here for just a minute, and we're going to use the ideal gas law to get these three. I'll be quiet, and I want you to get those three for me. On your mark, get set, go. Well, I got some answers. I got 600 here, 600 kilopascals, and I got 2178 for this one. Kilopascals. I got to check up on you guys. I got to make sure that people are still awake out there. Let me ask one of my wonderful students, Spencer. Spencer, do you have this pressure at state 4 yet? Do you have that yet, Spencer?
363.04 kilopascals.
That's what I got. So you guys are with me. I think we're doing fine. Now let's do this, the change in specific internal energy. That's what that is. Okay, well, here's the equation. It goes like this. Now this equation doesn't always work. It only works if you have an ideal gas, but we do. We can treat air like an ideal gas, so it's good. But see, going from 1 to 2, there is no change in temperature, so this is 0. And from 3 to 4, that's going to be 0 because there is no change in temperature from 3 to 4. Did you know that specific internal energy depends on temperature? The hotter the substance is, the bigger the energy. Kind of makes sense. But now to get this one, if you wanted from 2 to 3, you're going to have to put in, well, it would be what, 850? I know it's Kelvin, but the change in temperature from 2 to 3, well, it's 850 Celsius. But did you know that's also 850 Kelvin? If anybody wants me to, I'll explain why that is. But if you're okay, we'll just leave it there. Does anybody need help knowing that 850 change in Celsius is the same as 850 degree change in Kelvin? You okay with that? If you're okay, I'm okay with it. All right, well, let's get this then. I'm gonna do that now, and I want you to do it, and we're gonna find, by the way, what's this C sub B for air? I think it's, is it 7.717 kilojoules per kilogram Kelvin? Is that right? Yeah, I think that's right. All right, go for it. We're going to get the change in specific internal energy from 2 to 3. Here we go. Well, I got 609.5. Now these are kilojoules per kilogram. Kilojoules per kilogram. Now what about from 4 to 1? Well, you know what? It'd be the same. It's just negative. It's the same change. It's just that you're getting colder from 4 to 1. Does anybody need my help? I'll write that out if anybody asks. Okay. Nobody asks, so I guess you're all right. Now, 2 of these W's are 0. Two of these little W's are 0. And let me pick on one of my wonderful students here. Parker, unmute and tell me which ones of these work per masses over here are 0. Which ones are 0, Parker?
Would it be 2 to 3 and 4 to 1?
I like it. Good going, Parker. I think you guys are beginning to catch on to stuff in this class. Well, that's good. Now, how are we gonna figure the rest? Do you guys have any bright ideas? We need to fill in these boxes here. How about it? I'm listening for some good ideas. Go for it. Nobody said anything. Here, let me try this with you. What about this? We have an equation that goes like this, where the heat transfer, do you remember I gave you an equation like that? I think we derived it from scratch. Heat transfer is equal to the change in specific enthalpy. Well, that's heat transfer per mass. Now the question is, can we use that equation? Let me go to my good friend, Cameron. Cameron, this is you got a 50-50 chance, Cameron, of getting this right. Can we use this equation, heat transfer per mass equals the change in specific enthalpy? Can we use that equation to find the heat transfer in this column here? Cameron, what do you think? Yes or no? What?
No.
Cameron, you're right. You're a winner. But still stay away from the gambling, Cameron. It's not a good deal. But what am I trying to say? The casino, yeah. Stay away from the casino, yeah. But you're right. You can't use that. Now, Cameron, why is it that we can't use it? Now, there was a skull and crossbones on that equation here. Let me put the skull and crossbones back on there. There's a reason why you can't use that equation on any of these. Cameron, what is the reason? You're right. Cameron's right. You cannot use this equation, for instance, to find these heat transfers anywhere here. But why? Why can't you, Cameron?
Because there's no specific heat. I'm not sure.
Well, let me ask you this way, Cameron. When can you use this equation? When is this equation good? It's only good if you have a very special kind of process. What is that process?
Is it specific enthalpy?
No, that's not a process. There are different kinds of processes like iso thises and iso thats, but this only works for a particular kind of process, Cameron. What kind of process do you have to use this equation? Process. What kind of process do you have to use that equation, Cameron?
I'm not sure. I'm not seeing it in my notes.
That's okay. Aren't you glad I'm asking you that? Because you're going to have it in your notes now, if you're taking notes now. This works if you have an isobar. If you have an isobar, you're allowed to use that equation. Now, do we have any isobars? I want you to look. Let's see, we have an isotherm here, and we have an isochore and an isotherm. What about it? Do we have any isobars?
No.
No, so you can't use it. Can't use that equation. Forget it. Let's erase it right now. It's no good because we don't have any isobars. I find though, my students, they get a hold of an equation and they don't let a little thing like there's not being any isobars. They don't let that stop them. They go ahead and use it anyway. But then a funny thing happens. They don't get it right. Okay, well, we're back to asking you for you guys some advice. That didn't work. Do you anybody out there have any idea how to fill in those boxes? We got 6 empty boxes there, and we need to fill them in. I'm waiting for some advice. Well, this might be a long wait. Let me see. I'll pick on somebody else. Aubrey, help the class. Aubrey, do you have any idea how to fill in those empty boxes?
I know we can fill in a few using delta U equals Q minus W.
Good idea, Aubrey. Let me write that down. Aubrey's got a good idea. Did I write that big enough? Yeah, you can read that. Hey, look at here. We can get these two, Aubrey, just from here, because if you know this and you know this, well, you can solve for that. Now, Aubrey, this one's going to be plus or minus 609.5. Aubrey, you've got a 50-50 chance on this. Is that plus or minus, Aubrey?
It's positive.
Let me think now. Going from 2 to 3. Yeah, it's positive. Good going, Aubrey. And the reason why it's positive is you have a heat transfer Q23 going into the air in your piston cylinder. So it's positive. Hey, you know what? I think this here, they got the same numbers. This is going to be minus 609.5 for the same reason. You can use what Aubrey suggested. We know the W, we know the delta U, we can solve for Q. Yay, we did great. And that's the heat transfer out from 4 to 1. Good going, Aubrey. Now we still have four empty boxes. Let me go to one of my other wonderful students. I'm always picking on Stuart. Stuart, the class needs those 4 empty boxes filled in. Do you have any ideas how to do those? Uh-oh, Stuart's not answering me. He's probably tired of me picking on him.
Can we use CP delta T?
Let me try that. Now, there is a lovely equation that goes like this. We could get our delta specific enthalpy this way for sure. But that doesn't give you the Q, because see, the Q is not going to equal the delta H because we've just discussed that. There's no isobar, so I don't think that's going to help us any. Well, let's go to my next victim here. Spencer, we got 4 empty boxes here. What are we going to do? Got any ideas?
To find the work, maybe we could use RT ln V4 over V3.
That's it. Good going, Spencer. There is a lovely equation that we derived one day long ago, probably in June, that goes like this. Now, if you're doing from 1 to 2, you've got that equation right there. Now there's another equation. We don't want to get confused. There's another equation that goes like this. These are all in your book. I could show you the page number, but we have to decide when you can use this and when you can use this. Spencer, do you remember when you can use these different ones?
I don't remember the specifics.
That's what we're here for today. We got to know when you can use those, because equations are only as good as, I don't know how to express that. You can only use them improperly, and you can use them improperly. See, this one here is when your polytropic constant is equal to 1. And this one here is when your polytropic constant is not equal to 1. Well, going from 1 to 2, the polytropic constant is equal to 1 because P1 V1 to the 1 power equals RT, and T is a constant. And so P1 V1 is equal to P2 V2 to the 1. The polytropic constant is a 1 for process 1 to 2. This is the one we can use. You don't use this one Because if n is 1, you have a 1 minus a 1 in the denominator. And that is bad. Can't have a 0 in the denominator. You got to know when you can use these two equations. But we can use this equation here. Did I explain that n is equal to 1? Do you understand? From 1 to 2? Because see, the time is a constant, the temperature is a constant. Okay, well, I hope you understand. All right, let's go ahead and work this out. Here we go. We're going to work it out. The work from 1 to 2 is P1, 100 kilopascal, V1, 0.9274 times the natural log, 0.1546 divided by 0.92. Okay, now get your calculators out and plug that in, and I'm going to find the work going from 1 to 2, and we'll have this right here. Go for it. Let's see, I think I've asked everybody, and I'm back to Stuart. Take your time, Stuart, but we want to know what this little W is right here in this box. What'd you get? Do you have it yet?
I got negative 166.15.
That's what I got, negative 166.1. Now those are kilojoules per kilogram. We did great. And now we can use Aubrey's idea and solve for the Q. Because see, if you know two of these things, you can solve for the Q. I tell you what, the Q is going to be either plus or minus 166.1. Stuart, what do you think? Plus or minus on this heat transfer from 1 to 2?
Plus.
You had a 50-50 chance, and you blew it. It's minus. Now, the reason why it's minus is the heat transfer is going out. It's going out. And algebraically, look, if this is 0, and if this is minus 166.1, and there's a subtraction, and this is minus 166.1, algebraically, it works, doesn't it? Can you guys read that? I wrote awfully small. But see, there's a heat transfer going out. It's negative. So you want a negative right there. Now let's do from 3 to 4. We got 2 more boxes, and you know how to do them now. I'll shut up a minute and let you do those. What we're doing right now is we're filling in these last 2 boxes, and we're actually doing this equation from 3 to 4. Here, I'll put in the 3 to 4 for you. From 3 to 4. See if you can get the, see if you can get the work from 3 to 4. Let me find somebody here. Parker, have you plugged that in yet and gotten the work from 3 to 4, Parker?
Not yet.
Take your time. Here, I'll write it out for you. Let's see. P3 is 2178. V3 is 0.1546. And that's just 6. That's called the compression ratio. That should give you the answer.
Is it 56.16?
That's not what I got. Let me do mine again. Do yours again. I think I did mine right. Here's the numbers.
What about 262?
I wonder what you're doing wrong. I'm talking to Parker, right?
Yeah.
Parker, this is 2178. Hope you can read my writing. This is 0.1546. And this is just the natural log of 6. Put that in your calculators and tell me what you get.
I'm using my phone as a calculator.
That's
So-
okay.
I'm doing the log part right.
You should, maybe you did common logs. We want natural logs. Maybe that's the problem.
Yeah, I
That would
think-
be,
Never mind, I do.
there's a difference between natural logs and common logs.
.32.
That's more like it. 603 point, I got 3. I think we rounded off. Now, see, you can get this by using what Aubrey suggested. Look at here, if you know this and this, you can get that. And I'll tell you what, it's going to be a plus or minus 603.3. What do you think, Parker? Plus or minus 603.3 right here?
Plus.
Yes, it's plus. Good going. Excellent. Now, does anybody need help with any of that, or are you okay? All right, well, let's add these up and see what we get. I'm adding these columns up. 603.3 minus 166.1 I'm getting 437.2. Now let me add these up. Well, you're going to get the same thing. 437.2. And so if you wanted the efficiency of a Stirling engine, let's find that. I think they wanted that, didn't they? Let me read it and see. Now we're doing problem 1081. It says, they want the efficiency. They want the maximum pressure. Well, we got the maximum pressure. The maximum pressure is at 2,178 kilopascals. I didn't write it on the PV diagram, but I could. It's 2178 kilopascals. So we got that. Now let's do the efficiency. Here we go. Now the efficiency is a Greek letter eta. I think it's the 7th letter of the Greek alphabet. Alpha, beta, gamma, delta, epsilon, zeta. Yeah, it's the 7th letter of the Greek alphabet. And what it is the net work per mass divided by the heat that you have to pay for, the heat transfer per mass that you have to pay for. Well, what's that? Well, that's that 3,4 there. But now wait a minute. There's 2 heats that you have to pay for. This heat, you don't get that heat free. It comes from burning diesel or what, gas, or they have very many different kinds. They even have geothermal. They even have a geothermal heat source, but you have to get the heat from someplace. But see here, the total heat transfer is, you'd have to add the Q23. You'd have to add them up. See, there's 2 heat sources, so you'd have to add them up. So here's what you'd get. You get 437.2 over 2, 3, and well, you'd have to add these. That'd be 609.5 plus 603.3. Let me add those up and we'll see what we get here. 437.2 divided by 609.5 plus 603.3. Did you get 36%? We have a 36% efficient Stirling engine. Now, what they did back in the early days, and what they still do, is a very clever thing. It's called a regenerator. You see this heat transfer right here, this 4-1? They take that heat transfer out, and instead of just heating up Oklahoma with it, they recycle it around, and somehow they take that heat transfer, and instead of just wasting it, heating up Oklahoma, they put it back into the air inside your Stirling engine. Notice Q41 going out of 609. notice Q23 going in is 609. Hey, those cancel out, don't they? Interesting. And so what you have left, the Q, since we got rid of those, okay, I'm getting mixed up here. Yeah. The only heat transfer that you have to pay for is the Q34. That's a 603. So this is called the efficiency without a regenerator. I'll put without. There we go. Without the regenerator. But the efficiency with the regenerator, they call it a regenerator. Regenerator. Well, that's going to be your 437.2 divided by the 603.3. You still have to pay for that. That's going to cost you money. But these two here, you can save some money that way. Now, what that regenerator is, in the early days, it's like a big box with a bunch of real fine tin foil, a steel wool. Did you know that steel wool can heat up and cool off 50 times a second? Do you believe me? See, if this engine is running, is spinning 50 times a second, what is that a minute? What's 50 times 60? Is that 600? No, wait a minute. I can't do it in my head. It's too hard. 50 times, I think you're right. 50 times 60 is, you're right, it's 3,000 RPM, isn't it? That's what your cars are doing. You got 3,000 RPM on your tachometer there. Well, what we're saying is that steel wool, real fine steel wool in that regenerator, is heating up and cooling off 50 times a second. Gosh, that's pretty amazing. But so is the air in the engine. It's going from this 900 Celsius to 50 Celsius 50 times a minute. That's just a ballpark figure, okay? It might be going more or less than 50 times a second. But see, you can save some money that way. And here we're going to get the efficiency with the regenerator. That way, you don't have to pay for that heat transfer per mass. Isn't that nice? And they had these on the early engines, and they still do. Okay, I'm plugging this in now. And I'm getting 0.7247, which is what, 72.5% efficient. Man, that's pretty good efficiency, 72% efficient. The amazing thing about the Stirling engine is it's got a very high efficiency with the regenerator. In fact, it has the same efficiency as the Carnot engine. I need a little room to show you that. But before I do you have any questions so far? Well, okay, I guess you're pretty happy with that. Now, I need a little bit of room right, here's some room right here. Now we've done the efficiency without a regenerator and the efficiency with a regenerator. And a while back, we studied the Carnot efficiency. And I don't know if you remember this equation. It's in your book. These have to be in Kelvin. But that's the equation for the efficiency of a Carnot engine. Now let's just see. Now this is not a Carnot engine. But let's just see what the efficiency would be if you use these temperatures. Well, it'd be 1 minus, you'd have to have that in Kelvin. Let me put 50 in Kelvin. I'm getting 323.15. And then this would be the 900. I can't do that in my head. 900 plus 273. That would be 1173.15. Okay, now we're going to do that, and we're going to see what a Carnot engine efficiency would be operating between the same two temperatures. Okay, well, here goes. I'm doing that now. 323.15. And then you have to subtract it from 1. Well, here's what I'm getting. I'm getting 0.7245. Well, I think there's a round off thing, but look here. It comes out the same. It's a matter of a rounding off, I think. It turns out that the Stirling engine has a theoretical efficiency, if it ran perfect with no irreversibilities, equal to the Carnot engine. And the Carnot engine has the highest theoretical efficiency of any engine. And so that's one of the advantages of the Stirling engine. Now, let me tell you some other advantages. The Stirling engine doesn't have any wiring. There's no distributor. There's no spark plugs. In fact, here, let me diagram how it works. We'll give you a little 10-minute talk on how the Stirling engine works. I told you a little bit about the history. The steam engine became predominant over the Stirling. They were using these engines to pump water out of the coal mines. See, the miners would go down into the mines and mine coal. It was the age of 1850, around in there, and up till the turn of the century, 1900. And there would be water down there, and they needed to pump it out. And they would use Stirling engines, and they would use steam engines to pump out the water. They both had their disadvantages. The disadvantage of the Stirling was it had very high temperature. See, 900 Celsius is pretty hot. They had very high temperatures, and the metal would fail after a while. After 6 months or so, they would start leaking. They would have a problem, and they would have to shut it down. Well, shutting it down, and then they have to put in new parts. It costs money that way. And so that was bad. That gave the Stirling a bad mark, all due to the failure of the metal. Now, nowadays, they have wonderful metallurgy, and that's not a problem nowadays. So the Stirling is coming back. Now, The steam engine had problems too, though. The problem with the steam engine is you get terrific pressure built up when steam starts pushing against the container it's in. And if it's not built strong enough, it can blow up. And they've had many explosions. Steam engines have exploded. There was a steam locomotive over by Carthage, Missouri that exploded. The pressure got too much, and pieces of that engine, I forget how far away they went, but a long way, okay, mile or two. How would you like to be walking along and have a chunk of a steam engine come plopping down beside you? And so that was a big problem. People were being killed because of these explosions. And so that was a problem. But here's the thing, back in 1850, around in there, they didn't have all of the safeguards that they have now. We have OSHA, we have workman's comp, we've got all these occupational safety things, insurance. Back then, if someone was killed, hey, we need another worker, this one got blown up, and there'll be a whole line of people waiting to get their job. Times were tough in those days. So they went with the steam engine in spite of its problems. Let me show you how the Stirling works. I just need some room here. Now, is there any question from anybody so far? I'm open for questions here while I erase this. Now, on your final, we've studied numerous cycles. So let me tell you what they are. We've studied the Carnot cycle. We've studied the Rankine. And the refrigeration. We've studied Otto, Diesel, Stirling. You will have one of those on your final, but we've done them all, and I'm sure you'll do fine. And there'll be one of those tables of property tables with energy transfers with a lot of boxes for you to fill out. Each box is probably worth a point. And we've studied all those different engines, haven't we? Now let me tell you how the Stirling works. These are cycles that are going to be on your final exam. Now the Stirling engine it's got a piston cylinder. And see, this is the crankshaft, and it's spinning, and when it's spinning this way, the piston's going this way, and the volume's getting bigger. And then when it gets around to this position here, it's going that way, and the volume's getting smaller. And what they have is they have a very hot temperature right here. Right? They have a fire going right there. But but they also have a cooler area. It's still warm-ish, but it's a cooler area that's in here. They have something called a displacer. Now, it is not flush with your cylinder. It's called the displacer. Now, when the displacer is going this way, what happens is the cool air is pushed around here, and it makes the air inside your cylinder cooler. And when that happens, when it gets cooler, then the piston, the air contracts and the piston. Here, let me do it this way. When the displacer is going that way, the crankshaft is turning this way, and the piston moves this way, and the volume gets smaller. Now, when the displacer goes this way, what happens is this very hot air here is pushed around, and the air in the piston gets hotter. But you see, by that time, you're in a different position. You're like this. And the piston's turning like that. And the area is, the volume inside the piston's getting bigger. I don't know if that made a lot of sense, but that's the basic idea. They have what they call a displacer that moves back and forth, let's just say 50 times a second. This thing here is turning 50 times a second. And if they're in sync, that's the secret. The secret is to get the displacer and the crankshaft in sync. Well, they can do that. They're connected. The displacer is connected to the crankshaft, and it's going back and forth, and it's making the air inside the piston hot and cold 50 times a second. Does that make sense? And that makes it expand and contract 50 times a second. And that pushes the piston back and forth 50 times a second. That's the whole idea. Well, I showed you that. And we talked about the Stirling engine. Now, in the actual Stirling engines they have this separate. They have the working piston and the displacing. They have them separate. They have them connected. Let's see if I can show you that. Yeah, this is, they have the displacer separate from the piston cylinder. They're totally separate. But see, the air is contained in this displacer box and in the working piston. It's the same air. It can't get in, it can't get out, it can't get in. There's no mass that can get in or out. Whatever the air is that's in here and in this connection and in here where the displacer is, there's no air being added or subtracted from that. Nothing is said about a spark plug. I didn't mention anything about spark plugs. It doesn't have it. Stirling engine does not have spark plugs. That's kind of nice. It's simple, really.
Are steam engines pretty similar to a diesel engine?
Well, there's something you need to know about steam engines. Steam engines are external combustion. Steam engines are external combustions. The firebox, the fire is not internal, but see a gas, an auto engine or a diesel engine, for instance, is an internal combustion. I don't know if you've ever taken the head off of an engine, but there's crud in there and soot and carbon build up inside. You have to scrape it off with a putty knife. They're dirty inside. The reason why they're dirty inside is you're burning fuel inside the piston. Here, let me draw a piston for you. Here's a piston. And there's a spark plug right here. And there's some wires, and bam, there's an explosion in here. And you're burning fuel inside. See, auto and diesel cycles are internal combustion. And you don't always get a 100% burn. There might be some residue. There might be some carbon monoxide, even incomplete burn. But steam engines are external combustion. You can get a complete burn, and Stirling are too. Stirling engines are external combustion. And with external combustion, you can get a complete burn. You can get all the oxygen you need. There's no nitrous oxide or sulfur dioxide or all carbon residue. You can get a complete burn. Hey, Stirling engines are good for the environment because they don't produce the pollution. You know what produces pollution? Cars. Yeah, cars. Now they've come a long way to reduce that pollution with cars. I can remember going to Los Angeles back in the old days when smog was just terrible. They've really cleaned up Los Angeles. If you've been there, you can have clear skies and see the snow-capped mountains surrounding Los Angeles these days because they've made a lot of progress. But now you know there's external and internal combustion engines, and Stirling is an external. The nice thing about the Stirling is you can use any fuel. You can use, like I was telling you, you can use geothermal. You can even use solar. You can use solar. They have a Stirling engine that's powered by one of these, you've seen these searchlights, these big parabolic searchlights that shine up in the sky. You know, when they open a new car dealership, there's these searchlights shining up in the sky. Well, they take that and they focus the sun, and there's a focal point there that gets very hot if you focus the sun on that point. And they use that as their heat source on the Stirling engine. It's free. So you can run that as long as the sun's shining. Doesn't work too good at night. But you can use any fuel. Well, there's a little talk to you with you on the Stirling. Do we have any other comments or questions before we go on? Well, it's interesting. And if you are interested in the Stirling engine, just go to Google, type in Stirling, Stirling, Stirling engine, Stirling cycle, and you'll find pages and pages of stuff. It's got a lot of advantages. Now, what about disadvantages? Well, one of the disadvantages of the Stirling is it takes time for it to crank up. Like, that's the beauty of a gas engine car. You go out to your car, you turn the key, boom, put it into drive, and you can back out of your driveway. Well, with the Stirling, you have to build up that heat source. It takes a little while for that heat source to build up, to get hot, to run your Stirling engine, and that people don't have time to wait around. But there's ways to get around that. You could have a hybrid where you have a small gasoline engine to get you started, and then the Stirling kicks in. Anyway, it's a fascinating topic. Okay, we're gonna have a question or comment from anyone. If not, we're gonna take a 10-minute break here pretty soon and talk about other cycles. The topic today is after the Stirling, it's other cycles. Do you have any comments or questions for me? Okay, well, go stretch for 10 minutes. And we're going to talk first about this is really chapter 5. I'm kind of reviewing you here, especially because of, well, I think you need it, is why. I think some of you are perhaps confused a little bit about power cycles, refrigeration cycles, and heat pump cycles. That's what we're going to study after our break. We are going to study power cycles, refrigeration cycles, and heat pump cycles. That's the topic, next topic. Okay, go stretch for 10 minutes and we'll be back. Oh. Well, it's almost time to get back to work here. The first item on the agenda is the power cycle. And then we will do a refrigeration cycle and a heat pump cycle. There's another name for the power cycle. I don't know if everybody's back with me or not. But there is another name, and it's called the heat engine. Same thing, we'll put an equal sign there. They mean the same thing. And I use a schematic, I call it. I use what I call a cycle schematic. And for a power cycle, it looks kind of like this. And there's some equations that go with it. There's a actual efficiency equation, and then there's a reversible, or you could call it maximum if you wanted. It's the maximum possible efficiency if the thing ran perfect. And this equation goes like this. And that equation goes like this. These are all in your book. We've had them before, but I think it's worthwhile for you to understand them. And I'd like to do a problem. Now, this problem that I picked out is it's an example 5.3. It's in your book. It's called example 5.3. So let's dig it out and do it. And we're kind of having a review here. I don't know if everybody needs this review, but judging from the last test that you guys took, there's some of you that do. Some of you need this review. Okay, let me find this example 5.3. Okay. There it is. I found it. It's in the book there. Let me just see if there's anybody left, if everybody. Yeah, we got a good group. We got Bear with us now. Good deal. We got a good group. And if you tuned in late, we went over a Stirling cycle. Well, you could watch the YouTube over again. That wouldn't hurt you. But right now we're reviewing power cycles, refrigeration cycles, and heat pump cycles. Okay, now I'm looking at example 5.3 in the book, and it says heat transfer rate of 1 megawatt at high temperature 550 C. Okay, let me write it on my schematic. We got 550 degrees Celsius, and this heat transfer rate is 1 megawatt. All right, let me write that. 1 megawatt. You know, I'll put my megawatt in brackets there. Now I might need Kelvin. Let me find the Kelvin, just a minute. 550 plus the 273 that's 823 Kelvin. Now let me keep reading. I'm reading this out of the book. It's called Example 5.3. It's a power cycle, and it rejects energy to the surroundings, ambient surroundings. Ambient is just a fancy word for atmosphere at 300 K. Okay, well, this is 300 K. All right, 300 K. Work is produced at a rate of 450 kilowatts. Well, that's this here. This is 450 kilowatts. I'll put my units in brackets. See, this is not a unit here. This is the symbol for power. 450 kilo. We would like to know how much energy is discarded to the ambient surroundings. I think they want us to find this QL dot and the engine efficiency and compare those to a Carnot heat engine operating between the same two reservoirs. Okay. Now I'm not going to peek and look at the answers. They've solved the problem, but I'm not going to cheat. I'm going to see if I can figure out the answers without looking at them there. Okay. Well, the actual is, see, here's the problem. I don't know what that is. Don't know what that is. Well, no, wait a minute. I can figure it out, though. Look, 1 megawatt, you know what that is? That's 1,000 kilowatts. You got 1,000 kilowatts coming in, 450 going out. So you know what this has to be? This has to be 550 kilowatts because, well, if 1,000 comes in, these two have to add up to 1,000. That's it. Hey, we just figured out what the heat transfer rate was to the atmosphere. See, this is the atmosphere here. Okay, now let's get these. Well, you just subtract these. You got 1,000 minus the 5. That's 450. That goes here. And then you divide by the 1,000. And what you get is 0.45. Well, we just did the actual efficiency. It should be 0.45. Okay. Now let's do the reversible efficiency, or they call it the Carnot efficiency. Some people call it the Carnot efficiency. Okay. Well, that's 550 minus 300. Well, that'd be 250, right? 250. And then what is the high temperature? Well, you have to use Kelvin now. Here, see. Now, if you use Kelvin here, you'll still get 250. Do I need to explain how it doesn't matter about the change? Somebody speak up if they want me to explain that 250 better. But here you
No.
must use the 8.
Isn't the difference a lot larger because the 550 is in Celsius and 300 is Kelvin?
Yeah, let's do that. Is that my friend Spencer? Is that who that is?
Yes, sir.
Okay, Spencer, look. TH is 550 Celsius, which is 823.15 Kelvin. TL, I'm so glad you asked. Now, they never did tell us what it was in Celsius, but I'm going to get it. Just one tiny minute here. I'm getting 26.85 Celsius. See, that's atmospheric temperature, and that's equal to 300 Kelvin. Now, if you subtract these, wonder if I did that right. Did I goof up?
I think so. I was
I
getting
did. Hey, you're absolutely right. I'm going to give you a honking thank you point. I'm absolutely wrong. This is not 250. These will both give you the same answer when you subtract. I think when you subtract this, you get, is it 523?
yeah, 523.15 is what I got.
Yeah, I appreciate that. But now when you subtract these, let me do that. Should be the same. And I do appreciate you so very much. Hey, guess what? You get 523.15 when you subtract these. You get 523.15. Okay, now we're going to get the Carnot efficiency, and here we go. And you divide that by 823.15. And we get 0.6355, which is 63.6%. Hey, you know what? The Carnot efficiency, the maximum efficiency, is bigger than the actual efficiency. And I think that was my friend Spencer that got that thank you point. And we appreciate any student that stays awake during my discussions here and helps us. So now let's peek and see what they said the answers were. See, I haven't peeked yet. I'm going to see what they said. They said the efficiency is 0.45. Yay, that's what the book says. And they said the Carnot efficiency is 0.635. Well, I must have rounded off, but I'm pretty happy with that. And then they said that the power is 635. I'm getting confused now. I'm reading what the book says here. They said that the heat transfer rate, the low temperature is 365. We didn't get that. We got that. Well, I'm confused. I think we did everything correctly here, except up on the next page. I think what they're saying is instead of getting 450, if this was a Carnot engine, you would have gotten 636 or 635. That's what they're doing. They're showing you if the thing ran reversibly, what you'd get. Well, it's not going to run reversibly. It's going to run like this, and this is what you actually get. So I think we did everything right. Okay, that was a power cycle. And those are the equations. They're in your book, and we're going to do a refrigeration cycle next. Okay. Any comments or questions on that before we do the refrigeration cycle? Well, all right, I'm going to erase all this stuff. Okay, now we're going to do a refrigeration cycle now. And then later we'll do a heat pump cycle. So right now, we're going to do a refrigeration cycle. And this is example 5.4 in your book. It's example 5.4 in your book. Okay. Well, let's start with the cycle schematic. We're going to start with the cycle schematic. And you do that counterclockwise, like that. Everything is just backwards. The QL dots going into, here's your low temperature. Here's your high temperature. The QH dot is leaving your refrigerant. Did they ever tell you what kind of refrigerant? They never told you. What I have is R22 in my house, and you're transferring heat from your house, if it's a house, or your car, to the refrigerant, and then the refrigerant in the cycle will transfer heat out to the environment at the high temperature. Now, and then to do that, though, the catch is you have to input power. Okay, for those of you that just woke up from a daydream, we are doing problem example 5.4, and let me plug in some numbers. Here we go. It says here, air conditioner cooling a room on a hot day. Works as a refrigerator, show. 4 kilowatts removed from the room at 24 Celsius. I get the feeling that this is the 24 degrees Celsius room, and we're removing 4 kilowatts. Put those in brackets. Let me keep reading. To the outside atmosphere at 35. This is the outside. It's 35 degrees Celsius. We would like to estimate the magnitude of the required work. To do this, we will not analyze the processes inside the refrigerator, which is deferred to chapter 9, which we studied. We've done chapter 9. But we'll give a lower limit for the rate of work, assuming it is a Carnot cycle refrigerator. Okay, now I'm going to put this away and not peek. I don't want to see what the answers are. I want to see if I can do this without looking at the answers. Here's what they're doing in this. They're saying that they don't use eta, they use a beta. They're saying that the actual beta and the reversible beta, we're going to set them equal to each other. We're going to pretend that this is a perfectly no irreversibilities involved refrigerator. We're going to set them equal. Now the equation goes like this for the actual beta. You always have in the numerator what you desire. Well, what we desire is the QL. We desire the QL dot. That's why we bought the refrigerator, to remove heat from our house, let's say, or your car, or your hot dogs, or whatever you're trying to keep cool. And here you have to divide by the power. This costs you money. You have to plug in that refrigerator. Now, according to the first law, that's equal to QH dot minus QL dot. There's your equation for your actual, they call it coefficient of performance. Okay, now let's do the reversible. Now the reversible coefficient of performance, it's based on your Kelvin temperatures. And here they are. So what we're going to do is we're going to set these equations equal. Okay, well, let's circle the stuff we know. We know QL dot. Let me circle that. We know that. We know all the temperatures, only they have to be in Kelvin. So here, let's let me convert those to Kelvin. Hang on a minute. All right, I'm converting this to Kelvin, 297. Now I'm going to do this one in Kelvin. And it's 308. .15 Kelvin. All right. Now we know all of those. We know all the temperatures. Now, if you set these equal, oh, I know that. There's only one unknown. We can do this. There's only one unknown. Here, let me get this first. You would take the 308, and then you would divide by, wouldn't it just be 11? Did I do that right? What's 24 from 35? It's 11, isn't it? Yeah. Okay, let's see what we get here. I'm getting 28.01. And let's write our equation now. QL is 4. I'm writing my equation now. We all took algebra in school. I know we can do this. Here, let me shut up for a minute and a half. And I want you to solve for this heat transfer rate at the high temperature. I'm going to do it on a piece of paper. I can't do that in my head. So let's do that now. Go for it. See if you can do it. Did I get this right? Yeah, I think I did. Okay, I'm solving this now. What we're doing right now is we're solving this. We're going to find this heat transfer rate at the high temperature. well, I got an answer. Did you get QH dot is equal to 4.143 kilowatts? Anybody get that?
That's what I got.
Good.
Same.
Yay, I bet that's right. So now we know what that is. It's 4.143 kilowatts. And so now we can find the power required. Now this is the minimum power required. In an actual refrigeration cycle, you're going to have more than that, but this is what you'd have. Let's see, now we have 4 coming in, 4.143 going out. You know what this would have to be? It would have to be 0.143 kilowatts, because that and that have to add up to 4.143. So bottom line is, the power, the minimum power, the power is going to be it's going to be greater than or equal to 143 watts. That should be the answer. Now let's look and see. Now I'm going to peek and see what the book says. Okay, now they said they got a beta of 27. How come I got 28 and they got 27? And they got an answer of 0.15 kilowatts. We came close to their answers, but I wonder why they're slightly different. I think the whole thing is we use the 273.15 and they just use 273. I think that's it. See, they said 35 plus 273, and they got 308, and they divided that by 11. And when you take 308 and divide by 11, well, I still get 28. How'd they get 27? I think they made a mistake, actually. They did pretty good, but I think we did better. Here, let me write what they did. They're usually right is the thing that bothers me. I need some room right here. Here's some room. Here's what they did. They said 273 plus 24, yeah, over 35 minus 24. They said that's equal to 27. All right, now you do it. Let's see what you get when you do that. 273 plus 24 divided by, well, that's just 11, right? No, it is 27. I still think we did it right, though, because if you take 273.15, I think it makes us a tiny bit of difference. Or let's don't fuss over that. It's a matter of they rounded off. They got a pretty good answer. I'm pretty happy with that. Before we do the heat pump, I want to show you something else about my particular air conditioner. But did anyone have a comment or question about example 5.4. Well, okay. If you're happy with it, I want to tell you about my air conditioner. So if it's all right, I'm going to erase this. We're going to do my air conditioner for my house. And nobody said anything. All right. Well, goodbye. Example 5.4. Now I went outside to my house. And on my air conditioner, it said, well, first of all, there's these little plates there. And it said 24 amps on the there's a little plate there on my air conditioner. And it says 230 volts. 230 volts. We got the amps, we got the volts. And we've studied, I know we've had a course in this. Does anyone remember P equals IV? Let me go to one of my wonderful students here. Let's see. Bear, did you ever see that equation, power equals current times voltage? Have you ever seen that, Bear?
Yes, sir. I saw it in physics.
Yeah, absolutely. You'll see it there, or you'll see it other places. What I want you guys to do is to find the power. Now, what that is the power that's going in. Remember the schematic? You're going counterclockwise. We're talking about that's our secret symbol for power. See that W dot? That's our little symbol for power. Now, this is what they use in physics and other classes, but we're talking W dot, which means work per time. That's what power is. So I'm going to shut up and I want you to tell me the power. We have, look, we have the amps. That's, I don't know why they pick I for current, but they do. And we have the volts. We have the amps, we have the volts. So what is the power? Go for it. You have 30 seconds. All right, now let me pick on one of my wonderful students here. Aubrey, I'm back to Aubrey. Aubrey, what'd you get for the power on my air conditioner?
I got 5,520 watts.
That's exactly what I got. Now we might want kilowatts, so here, let's make this 5.520 kilowatts. Okay, great. We just figured this out. We'll put a circle around it. We got that. Now, this right here, this QL dot, they have a name for that. They call that the oh gee, having a little trouble here on my memory. It's called the refrigeration capacity, I think is the name of it, and it's measured in tons. Now, what I have a 4-ton heat capacity, I think is a fancy name for it. All it is the QL dot. It's the heat transfer rate from the from my house. In this case, we're having a heat transfer from my house, and we have a 4-ton heat transfer. Now, I'll explain why they call it that. Well, I'll just tell you. It has to do back in the days when they had ice houses. Well, they still have ice houses. But what a ton of refrigeration is it's the heat transfer rate to freeze a ton of water at 32 Fahrenheit or 0 Celsius. See, if you have a ton of water and you want to freeze it, you have to remove heat energy from that water and it will freeze. It won't freeze unless you remove the heat energy from it. And 1 ton of refrigeration is the amount of heat transfer rate in 24 hours that will freeze a ton of water. That's where they got the name ton of refrigeration. But here, let me tell you what it's equal to. It's equal to, let me write it over here. 1 ton of refrigeration. We probably should write of refrigeration. Is equal to 211 kilojoules per minute. Now, we need kilojoules per second. So, see, that's a kilojoule per second right there. If you wanted this in kilojoules per second, you'd have to divide by 60. Let me see what that is. It's 3.52 kilojoules per second, or in other words, kilowatts. That's what a ton of refrigeration is. Well, I've got a 4-ton unit on my house. And so if I have 4 of these, I tell you what I have. I got 4 times that. So multiply that by 4. What I have is 14.07 kilowatts. Okay, so here's what we got. We got 14.07 kilowatts coming in. We have this is 5.52 kilowatts of power that I'm having to pay the electric company. And this is, I can't add those in my head. Let's see. Plus 5. This is 19.59 kilowatts that I'm making Oklahoma hotter, because if you go outside my house when that air conditioner is running and just put your hand over the condenser, it's blowing hot air. I'm making Oklahoma hotter. Okay, so now let's calculate the efficiency of my air conditioner. I want the actual I want the actual efficiency of my air conditioner. Now you have all the amounts. I didn't put the temperatures on here, but we're just doing the actual. You don't need the temperatures to find the actual. Go ahead. I'll shut up. I want you to find the actual. It's not efficiency though. It's called coefficient of performance. Find the coefficient of performance of my air conditioner on my house, and I'll be quiet. Stuart, do you have that yet? Stuart, do you have the actual coefficient of performance of my air conditioner on my house?
I got 2.551.
That's what I got. Now that doesn't have any units because it's just a ratio, okay? And it's not percentage. And there's something about this you need to know. This is always, it's always bigger than 1. Coefficients of performance are always bigger than 1, and efficiencies are always less than 1. But there's my air conditioner, and you could figure yours now that I've showed you how to do it. You just have to read what it says on there about your amps and your volts. Okay, now we've done, does anyone else have a comment or question before we do a heat pump? Well, okay, if you're happy. Got to review some basic electrical stuff there, didn't we? Wasn't that fun? All right, we're going to do a heat pump. I'm going to erase this unless somebody speaks up. Okay. All right, now we're going to do a heat pump. Now let's go over the schematic first. Now the schematic looks exactly like a refrigeration cycle. It's counterclockwise, round and round. All the arrows are going like this. This is QL dot. This is your low temperature. This is your high temperature. See, what's different about the heat pump is this high temperature is what you want. You want to keep your house warm in the winter. That's what you want. See, with the refrigeration cycle, what you want is to remove the heat from your house and keep it cool. This is what you want. But here, it's the heat transfer rate at the high temperature that you want. The only problem is it costs money. You've got to pay for it. Because Mother Nature doesn't like transferring heat energy from cold things to hot things. The way Mother Nature likes to do it is to transfer heat energy from hot things to cold things. It has to do with molecules and their vibrations. When they're hot and cold, I think they vibrate faster when they're hot and vibrate slower when they're cold. Okay, we're going to do a heat pump problem. Now this, we need the equations here. Let's write them. I think this book uses a beta prime. And there's an actual. And there's a reversible. Beta prime. Now the actual, what it is the QH dot divided by the QH dot minus the QL dot. The reversible is the TH all over TH minus TL. There's your equations. They're in your book. They're in your notes. We've done them before, but I'm a believer in repeating stuff. Maybe if we repeat stuff, we'll get it. Okay, now what I'd like to do is I'd like to do problem 593E. It's English. We need to know how to work in English, you know. Just because everybody else in the world, almost everybody, uses SI, we still use English here in America. And we're looking at 593E now. Let me see if I can find it here. 593E. Found it, 593E. Okay, this is a problem in your book. For those of you that just woke up from a daydream, we're going to do problem 593E. It's in English, senor. It says a large heat pump should upgrade 4,000 BTUs of heat at 175 to be delivered as heat at 280 Fahrenheit. Okay. I get the feeling this is the lower temperature of 175 Fahrenheit. And this is the 280 Fahrenheit. That's the feeling I get. What is the minimum amount of work, power, input that will drive this? I think it's kind of like that last problem. We're going to have to set these equal. We're going to set them equal. But don't we have to know something else? Let me read it again. Oh, yeah. 4,000 BTUs. I get the feeling this is 4,000 BTUs per minute. Is that what it is? No, per second. I wonder if that's what they mean. I think that's what they mean. Okay, well, let's try that and see if that's it. Now, I'm not going to look at the answer. I do have an answer book, and we can look at that in a minute. But let's work the problem. Let's circle the stuff we know. We got to have this in Rankine, guys. Roughly, I'm just going to do like they do. Roughly, you add 460. It's really 459, 67, I think. But I'm going to be kind of lazy and put that in Rankine. Now, let me do this in Rankine. I believe it's 740 Rankine. So, hey, we know all of this stuff. Let me plug it in and see what I get here. That's 740 Rankine. And the difference is, is it 105? Let me make sure I didn't goof that up. Let's see. Yeah, that's right. Now, if you have any questions, just ask. Okay. Now we're going to set these equal. Now let me see what this is. 740. I'm getting, this is equal to 7.048. So what we're going to do is say 7.048 is equal to QH all over QH, well, there's dots on it, minus the 4,000. Okay, those are BTUs per second. All right, well, we're going to solve that, algebra students. Let me shut up for a minute. And when I did this before, I got a different number here. Just a minute. I might have goofed up. I think I did that right. But let me double check. No, I'm getting a different number here. Okay. No, I think we did that right. I believe we did that. Okay, I haven't figured this out yet. I can't do that without pencil and paper. So let me work on it. I want you to work on this and give me the answer. Well, I wonder if this is what you got. I tried to solve this, and I'm coming up with the heat transfer rate at the high temperature is 4,661 BTUs per second. Did anybody get that? Is anybody still with me? Let me look and see if there's anybody still out there. Yeah, there's a good crowd out there. You guys are faithful. You're sticking it out. Proud of you. I wonder if I did that right. Well, let me check it and see. Well, I'll know here in a minute. Yeah, that looks pretty decent. Okay, guys, we've just figured out the heat transfer rate at going to your house. And this is the heat transfer rate coming from the environment. Well, actually, this is not atmosphere. This is some manufacturing plant or something, because we don't have temperatures of 175 Fahrenheit in Oklahoma. They might get up to 105, but not 175. But this is a heat pump, but we're not warming up your house, okay? I mean, gee, if your house was 280 Fahrenheit, you'd be dead. You understand? It's a heat pump, but it's not, in this application, warming up your house. But we can get the power necessary, the minimum power necessary to operate this heat pump. If you know this is 4,000, and you know this is 4,661, then this is 661 BTUs per second. That's the minimum power that you're going to have to operate that heat pump. Now, I don't know if I got that. I got an answer book here. Let me look and see if I have that one. What is that? 593E? I might have it. We'll look and see. I don't think I have that particular one. You're just going to have to trust me that we did that right. All right, well, we've done all three now. I've shown you those equations. We've done a heat pump, heat engine, and refrigeration cycle. Did anyone have a comment or question on anything? Okay, well, you'll find your homework should be available to you. I think it's due Wednesday night. You'll get your final exam Wednesday morning. It's due Saturday night. And Wednesday is going to be another review day. I'm going to go over, I'll tell you what I'm going to go over. You could study it if you wanted. But I'm going to erase this first. Do you have any questions about this? Okay, we're going to say goodbye to this. We did a heat pump. Do you notice that the schematic is identical to the refrigeration cycle? The only difference is on the refrigeration, you want this down here. This is why you have it. With a heat pump, you want this right here. This is why you have it. That's the difference. And the equations are different for the betas. The fancy name for this is coefficient of performance. Okay, well, let me say goodbye to 593E. We did a heat pump. Let me just mention one thing about a heat pump. I wish I had one. Really, the key idea, I don't think I've ever told you, the key idea, let's say this is 2, this is 3, and this is 5. And they could be megawatts, okay? I'm just making that stuff up. This is what you have to pay for. The 2 megawatts here, that comes from the PSO. You get a bill at the end of the month for the electric bill. They want you to pay them. But this is free. What this is it's heat transfer for a cheap heat pump. It's just from the atmosphere. But if you have one installed where they transfer heat from the ground. See, if you'll dig down in the ground, 4 or 5 feet, put your coils down there, that temperature stays warm relatively all year long. Well, it doesn't change much. If you dig down about 4 feet in the ground, 5 feet, the temperature doesn't change much. It stays about the same all year long. Now, it might be wintertime, and it might be 5 degrees below zero with snow on the ground. But if you dig down 4 feet, it might be 60 degrees Fahrenheit. Not zero. It might be 60 degrees warmer and down there in 4 feet deep than it is on the surface. That doesn't cost you anything, and that's the beauty of these. If you have one that has your coils down there in the ground, that 3 megawatts is free. No charge for that. And that's why you can save money if you have a heat pump system. If you don't dig down, if it's just removing heat from the atmosphere, it still saves you money. Now, the bad thing is it costs money to put in a heat pump. Once you get it installed, then you start saving money. Okay, now Wednesday, here's what we're going to do. We've had these equations here that we know and love. We derived these equations from scratch. And there's another one just like it that goes like this. And Wednesday, I thought we'd review those two and talk about when they can be used. See, it's one thing to have a lot of equations at your disposal. Like that one earlier we talked about with the skull and crossbones. Remember this one here? It's a lovely equation. But when can you use it? If you use these equations on the wrong application, you don't get the right answer. We have to know when you use these equations, when you use the tables in the back of the book. It's kind of a review. I think it'd be good for us on Wednesday. If you want to study those over so you'll know what I'm talking about on Wednesday, that would be good. Well, I've told you about everything I want to tell you for today. Wednesday's a review day. You have homework and exam coming up. Did anybody have a comment or question? Well, if you don't have any comment or question, I'm going to push this little red button here in a minute and go eat some lunch. This is your last opportunity. 5, 4, 3, 2, 1. Okay, bye-bye for now, students. I'll see you Wednesday.